Share that's recording. Okay, perfect. All right. So good morning for the one of you that is here, or good afternoon, I guess, at this point. So in this tutorial, we're going to be working through a little bit more of projectors and trying to see how we can get a little bit more of a grasp on them and like more of a practical usage of them for doing questions. We're still like using projectors to build up to the actual implementation of the Merman experiment, but for now we're hoping to get a better sense of them by doing some questions with them. So some practical, actually, like let's do some questions and see if we can work through them just so we get more comfortable with projectors in general. So to start off, I did want to point out in the book that Dr. Sabri pointed to me that there is, if anyone's like confused about the block sphere, there is a section in the book that covers like and talks about the block sphere, 2.5.2 on page 23. So if you go to page 23 in the textbook, you will see that it does give a little bit more of a geometric like perspective. He was talking a little bit in last time, but just in case you wanted another overview on it, this helped me a little bit to see also like on the poles there's like the imaginary, and then there's also these other vectors they define, which is plus and minus. We haven't talked about those in class, but it's just kind of giving like an intuitive sense of where everything might be geometrically, and then the 1 state and 0 state obviously at the north and south pole. So that is just in the textbook for reference. If anyone needs it, not required reading, but just in case, if you want to learn, like think more about it from a geometric perspective when we're talking about single qubits in the block sphere. But today, more importantly, before I get into stuff, any questions from anything, assignments, like projectors or anything like that? All right, cool. But if there is, please feel free to interrupt me about anything. Today, we are going to be doing exercises. So section 4 is kind of covering like all of the textbook is what we're covering pretty much today. It goes from like bracket notation and then projectors, but we're going to be starting with some exercises. So let's go to page 47 first. So yeah, in the textbook it goes through just a quick overview of like how projectors work and like how they like their matrix form. And with that, we're going to start off with some very simple exercises. And let's scroll all the way down to the bottom past that section. I think it was page 66, so where the exercises began. Yeah, let me just type in 66. That's the one. Okay. So we're going to start off real basic and then getting a bit more advanced. And I wasn't sure how to do this because I don't have a writing pad, so it'd be easier to show it like matrices with a writing pad, but I'll try to do my best between OneNote and Excel. So basically what we're going to be doing is I'll define a couple different things just to make sure, and then we'll get into actually we're going to start with question 4.1a. So the question says, so given the bracket notation here, in the standard basis, which I'm not quite sure what the standard basis is, but all I know is we're just using, you know, our normal convention of what we think like 1s and 0s is, or the 1 state is. Like we have to give the matrix given the bracket notation. So we'll start with this one here. Throw that on the side and throw this on the side. We're going to have to translate, and I'll make this a little bit bigger, translate this guy into bracket notation. So any ideas off the top of your head, or do you know that off the top by heart, or do you want me to go through the whole, like, not derivation, but at least show the thing, or like the steps on how to do that?
What's plus again?
Oh, not sure, actually. So I tried to look up what plus and minus are, and I have no idea. I was just going to skip over the ones with plus and minus, but that would be an interesting question for Dr. Sabri. Because I did not look that up. I mean, I could look it up in the textbook real quick and see if anything comes up, but I'm not sure what those are defined as.
Yeah, I think I remember mentioning.
It might be related to the spin states we're going to be working on, or working with soon, or like the spin operators. And it might define it in this section.
I remember him saying this is normally called plus. And this is normally called minus. I don't see that.
Yeah, not sure off the top of my head.
Maybe he didn't go over there, maybe I just imagining.
Yeah.
Okay.
But
Let's skip this one.
we can ask him. I mean, I saw when it was like if we look back at the block sphere. Well, wait, no, not that. Was it 47? 47 maybe? No, I forget which page it was. The block sphere, page 23, it had a plus and minus on the block sphere right here. So it had plus on one side and then minus on another side, and then the imaginary, and then and the negative of the imaginary. So I'm assuming it's some kind of superposition state of something, but not sure what. So.
Yeah. No, I don't know.
All right, no worries. That's a question for Dr. Sarb. But anyways, we'll be skipping B just because I don't know what plus and minus are. So if we learn what those are, it's possible to do it. But yeah. All right, so let's start with question A, though. See what we can get. So any ideas how to approach converting Bra-Ket into matrix notation off the top of your head? If not, I'll work through the steps.
I think if it's a vector, if it's like this way, I think that's bra, right?
Yes. So
Like the first one, so within this, like the A would be bra and then cat, right?
yes, absolutely.
Yeah, okay. So bra would be bra's a column vector, right?
Yes, absolutely. So this will be, I'll try and draw it or like write it out in that form. So it'll be like 1 and then, oh wait, that's not gonna how it's not gonna work. Be like 1 and then 0.
Yeah.
Yeah, exactly like that.
And then cat would be the row version of that.
Yeah, absolutely. So yeah, whenever you flip it, yeah, you're right. So whenever you flip or like turn from a bra to a ket, it's basically you're just doing the transpose of it. So it would just look like that, like you set a column and row vector, and I'll draw the little vector signs around it, hopefully in a reasonable form. So something like this. Yep, absolutely. So if we were to do the matrix multiplication on that, then what would the like combination of the multiplication of the bra and the ket, what would that equal to? Is the question. So this guy is a 2 by 1, and I will say that this guy is a, oh sorry, no, he's a 1 by 2, sorry. This guy's, no, get that right?
I think it's 2 by 1.
Yeah, I think it's 2 by 1. But we're multiplying a 2 by 1.
1 by 2, so it should give you a 2 by 2.
Right, yes, it should give us a 2 by 2. Yes, so it will be a matrix. So if you remember how to multiply matrices, it should be a 1, so I'll actually try and make it actually look like a matrix in the notebook. So we're starting off with a 1, 1 by 0 multiplied by a 1 by 0, but in the opposite direction, so it's not going to let me do that. There we go. Let's try this. So 1 by 0 multiplied by a 1 by 0, but in transpose. So when we do it in the actual matrix, like what the matrix will go about to be, what we do is we multiply the first one by the second one. So like the first like row by the second, or by the first row of the first matrix by the second row of the second column. I had to like bring up the like actual like matrix multiplication. Where was it? Matrix multiplication. Just because I always forget how to do these, even though it should be simple at this point. I'm not sure if I have permission to show this, but hopefully it's okay. But yeah, when we're doing matrix multiplication, you multiply the first row by the first column, and then the first column by the second row, and so on and so forth. So if you were to actually multiply that out, we're going to multiply the first row by the first column. So the first row is going to be a 1 multiplied by 0 plus 1 times 0, so that's going to be a 1 there. Then the second one, oh sorry, that's just a 1 times 1, that's my bad. Then the second one is going to be 1 times 0, because you're multiplying the first row by the second column, so that's that. And then the next one will be multiplying the second row there by the first column, so that's 1 times 0 is 0. And then the last one will be multiplying the second row by the second column, so that's 0 times 0 again is 0. So the first question, question A, is this is the matrix form of the operator that we are working, or the, like, you can call it a projector, but yeah, it's the outer product of these two these two versions of the bits essentially, but it's actually more of a projector because it's a matrix. But in this case, we're not we may be strange that we're working with matrices because we're going to try to get away from matrices, but we're going to build up to the intuition of how we can multiply this Bourn notation, just kind of give a sort of a basis for it. So now let's move on to the exercise C. So exercise C, what we're going to be doing, and I apologize, it's going to look weird in OneNote. We're going to first start off with what the bit for 0, 0 looks like. So do you remember off the top of your head what 0, 0 looks like? If not, no worries.
So that one should be another column vector, and it should be 1, 0, 0, 0, right?
Yep, absolutely. So that's 1, 0, 0, 0 right there. And then yes, if you take the transpose of it, that's flipping the rows and columns, so that would equal 1, 0, 0, 0. So we're adding another bit, and we're adding another dimension, as Dr. Sabri likes to point out. Like this would correspond to the 0, 0. My writing is horrible. This is the 0, 0. This is the 0, 1. This is the 1, 0. And then this last one is the 1, 1. So like in our last example, you just place a 1 wherever the corresponding bit or the corresponding number would be, or the output to input. So because it's a 0, 0, we place a 1 in the 0, 0 to designate that it's 0, 0, and then when we flip that, it's just the opposite way around. So now what we're going to want to do, so to get C, we have to multiply a 0, 0, and then add to it a 0, 1. So let's start by multiplying the 0, 0 by the 0, 0. So what that will look like is 0, 0 by 0, 0. So this one, I'm going to try and combine the matrices again here. So let's, actually we're going to have to make a bigger version of this guy. So it's going to be a 4 by 3, so that's 1 by 1, 0, 0, 0, and then we're going to go 0. Oh, that's not it. Go through all these, 0, 0. So yeah, this is us multiplying these two matrices together. And then, what's that, sorry?
Why is it 1, 1, 2?
Oh, sorry, yeah, this is just because I think of this should be a separate matrix, and this should be like the row vector, and this should be the column vector. I made it a big matrix here. I wish I could delete these rows. I'm just trying to represent. No, I know, it's weird. I should really separate them. I was going to think about doing it in Excel, which actually might be easier to show. Maybe I should start doing it in Excel, actually. Just because
that's like the column vector.
Yeah, and this is the row vector. So yeah, I'll start doing my work in Excel just to make it more explicit. Yeah, sorry about that. I wish I had a writing pad to actually show it. But yeah, let's actually, and then I'll put the formatting tool there. Charts. Yes, yeah, we'll do it like this, and then we'll do it like this, and hopefully that's a little bit better to explain that we're multiplying two matrices together. So, or multiplying two vectors together, essentially. So, if we multiply these two together, making equals there, we're going to start by multiplying each of the indices. So it's first row by first column, so we'll get a 1 there. And then it's obvious that since we're multiplying each of the row by 0, it should get 0 for the rest of them. And then it should be obvious because we're taking a 0 for each of the rows and multiplying that by each of the columns, then we're just going to get a 1, 0, 0, 0, 1, 0, 0, 0, and a 1, 0, 0, 0. So yeah, just simple. I know it's trivial for now because we're just multiplying two vectors, but for now we are just starting off. This is what our this matrix or this Bourn notation is essentially denoting here. So now, because in our question C, let me pull back up the question, we have to add 0, 0 plus 0, 1. We need to calculate what 0, 1 is. Let me paste this in here just to make it, oh, that's not good formatting. Let's just write it out just so it's a bit more clear. 0, 0 plus 0, 1, and 0, 1. So let's now work out what 0, 1 is. And I will do that back in Excel so it makes it a little bit more clear. So 0, 1, I'll 0, 1 there. So that is just going to be another column vector, except here it's going to be a 1 in the second slot because this is corresponding to the 0, 1 slot there. I'll make that nicely formatted. Then if we look at the 1, 0 case, or the 0, 1, but now in the ket, it is just going to be a row vector that is going to be 0, 1, 0, 0, because we just flipped the rows and columns. So if we were to multiply these two together this time, and I'll copy these two just to make it look nice, 0, 1, and then 0, 1, we're going to get a 4 by 4 matrix. I'm just copying this just for reference. We'll clear these. So we're going to get a 4 by 1 matrix. The first row is going to be all zeros because we're multiplying each of the ones by zeros. The next row is where we finally going to get our first one. So 0 by 1 is 0, but then 1 by 1 is 1, and then the rest of them will be zeros, so multiplying by 1s, and the rest of the matrix will be 0. So we can start to see a pattern here that whenever we get like a bracket of the same thing combined, we're going to get something on the diagonal, because corresponding to whatever the actual, like whatever the position is. So 0, 1 is the second position on the diagonal, 1, 0 is the third position on the diagonal, and 1, 1 is going to be the fourth position on the diagonal, just because that's how vector notation or vector multiplication works. So now what we have to do to get the final question is we're just going to add these two matrices, which would be straightforward to do. So we'll do this plus this, and all we're going to do there, because it's just a matrix, we just add each of the elements of the two matrices together. So if we add this guy plus this guy, the only thing that will change is there will be a 1, 1 in the first two diagonal slots. So this should be equal to that matrix. I'll actually formally write it out here. So this matrix plus, I'm going to have to put a comma there because or else Excel will think I'm making a formula. So this matrix plus this matrix equals the following matrix, where it is a 1, 1 on the two diagonals. So hopefully that makes sense. It's just matrix multiplication addition. I'm doing this more so also for me because I forget how to multiply matrices and vectors, so hopefully that's straightforward enough for now. Then the next one, question D, we're only going to do up to D for these exercises. Given this bracket notation, we're going to make this bigger one. Thankfully, if you look at D, we've already done a bunch of the work there because we've already done the first half of the addition. So we're starting off with this matrix here, but then we're going to add some new elements that we haven't calculated out, ones where it's not the same bracket notation there. So we're going to get some different matrices that we haven't multiplied there. So we're going to start off, I'll put the Excel spreadsheet on the right hand side, and then we're going to start with question D. Sorry, I'm flipping between the two things. So we already have this matrix here because we know that this matrix is this part of the sum, this part. So now we need to calculate the second half of the sum, which is these two terms here. So we know from before, thinking about it, that 1, 1 is going to be a column vector, or sorry, a row, column vector, yes, a 0, 0, 0, 1. And then the 1, 0, is we've seen before, is going to be a row vector of 0, 1, 0, 0. So I'll make these two into matrices, make it full screen so I can actually see the button. There we go there. So now when we multiply these two matrices, what we're going to get, there's going to be no multiplication in the first three rows. So I'm going to copy this just for reference. Copy this guy. So there's going to be no multiplication in the first three rows because we have the first three zeros here that are multiplying. No multiplication there. And the only part that we're going to get our first 0 is in this section here, because it's first we're going to do 1 times 0, and then 1 times 1. That's where we're getting our first 1. So this is the matrix that we get here for 1, 1 multiplied by 1, 0 ket. So yeah, bra 1, 1 by ket 0, 1. Then we can do our next part, or our next operation, which is 1, 0 times 1, 1. Then we're going to do that here. Now this is going to be 1, 0 times 1, 1. So this should be pretty straightforward and known by now. This is just going to be the column vector, but where it's in the third position, because it's counting in binary. So again, this is the 0, 0, this is the 0, 1, this is the 1, 0, and this is the 1, 1 positions. So I'll erase those just so I can do it. And then this is going to be the row vector with a 1 in the last position because it's 1, 1, and we're transposing, like the column vector transposed over. So then, when you multiply these two together, we're going to get, again, zeros for the first couple rows. So I'll make this reference, delete it. 0 for the first row, 0 for the second row, because it's all being multiplied by 0. And then the only thing we're going to get is a 1 there because it's the last, the third row and the fourth column multiplied together is where we're going to get our 1, and then just a bunch of zeros there. So if we were to add all these matrices together, so we're starting off with this matrix, and then we're adding this matrix, and then this matrix. Hopefully it should be apparent, but I'll write it out here. So it's this guy plus our next two terms, which are the 1, 1, 0, 1, plus the 1, 0, 1, 1 equals this next matrix, which is just going to be the combination of those two on the diagonal, plus we had 1 down here from this guy, and then 1 over here from this guy. So if we were to translate this expression into matrix form, we will get this matrix right here. So it's just to show, there's this notation is a fast and convenient notation to represent large matrices without having to multiply them out. As an exercise for this week, I'm going to leave you this one, section 4.6e. So that's part of your homework for this is 4.6e, which is multiplying the phi notations there, and just to see that what it would look like when we do like an actual projector of 0, 0 plus 0, 1. So I'll leave that as an exercise for you guys to hand in for this Saturday. All right.
Should we multiply the halves into the matrix as well, or should we just leave it like that?
You can leave it on the side if you want to, but also feel free to multiply the halves in there. It'll look cleaner if you just leave it on the outside, so feel free to do that, but if not, no worries. But good question, yeah, because it obviously will look a little different. As you see in the textbook, they decided for the next one to multiply the halves in, but I don't mind. Either way works. But yeah, so I'll leave that one as an exercise. But now we're moving on to the next one. So we're also going to do some of the exercises from 4.2, and this is going to be, at least for me, a little bit more the interesting one, where we're going to take the following matrices and translate them into bracket notation. So thinking about how we do the reverse of what we just did here. And hopefully that should give a little bit more of an intuitive understanding of how these projectors work. So in 4.2, we're going to start with 4.2a. We're going to take the Hadamard operator, which is this guy over here. So if we remember, it's actually just because we multiplied those in. It's the 1 over square root of 2 times 1, 1, and then 1, negative 1. And that's because, I'll bring this out a little bit here. This one is the 0, 0 bit. So if you remember, this is the 0, 0, and then this is 1 here, and then this is 0, and this is 1. Then this is 1. Yeah, if we remember from Hadamard of 0 equals what would be this column vector here, which is 0, or put the 1 over square root of 2 in, but it would be 0 plus 1, or the 1 bit there. And if we do Hadamard of 1, we're going to get this column here, which is the 0 plus or minus 1 here. So 0 minus 1. So it's just basically what we've done with this matrix here is condense it down into a, condense our Hadamard down into a nice convenient form. But what we're going to want to do is now represent this in bracket notation. So any ideas how to take a matrix and throw it back into bracket notation?
Other than just guessing, I don't really. guess, like educated guessing.
Right. No, no, absolutely. Yeah. It took me a second to think about how I would work back these as well. The way that we're actually going to be doing it is we're going to imagine adding up all the matrices that have all these different positions here to make it, which hopefully makes enough sense. So remember,
That would be something like 0, 0, and then 0, and then like 0 and 1, and then like 1 and 0, and minus 1 and 1.
yes, sir. Absolutely. Yeah, you got it right. Yeah, great picking that up right away. So yeah, before, where was our single bit? Oh, we did it. We did it in the OneNote. But yeah, before our 0, 0 gets us the first position, like exactly like you said, Chris. So like we're working with single qubits, so that makes a 2 by 2 matrix. So 0, 0 is equal to 1, 0, 0, 0. So we get this old matrix here, and that's we see that's going to correspond to the first one. Then if we do 0 and then 1, just like you said, it will equal to 0, 1, 0, 0. So that's where we get our second one there. Then the Ket-Bra combination 0 or 1, 0 should be 0, 0, 1, 0. And then the last one is going to be 1, 1, which is where we get that diagonal or the 2, 2 position, 0, 1, which is equal to 0, 0, 0, 1. So I'll just make those into separate matrices so they look kind of nice. I guess they're kind of going to blend together if I don't. I'll insert a row in between each of them just so they're clear that they're separate matrices. Throw that in there. So yeah, absolutely. To now throw this back into like now we can like use this and just make a big sum of these to get the like answer we want or the Hadamard we want. So we got to remember there's a 1 over square root of 2 term out in the front, but then we're going to multiply. I'll put this in proper brackets so it actually looks like it's doing something. So then that's multiplied by all of our matrices in here. So we're going to take the 0, 0 bracket, 0, 0 inner or outer product. Oh no, sorry, the 0, 0 plus the 0, 1. It's exercise in typing here. Plus the 1, 0, and then subtract the 1, 1 case, or the 1, 1 bracket, and that is our Hadamard there now in bracket form. So that's how we can see if we were to, you can also guess, like check this, because if you multiply in the 0 case here by a Hadamard operator, so if we actually use this, so h is equal to this thing here, h is equal to that. If we were to do h and then multiplied by the 0 case, or like the 0 bit, where the 0 bit is like we can either do this in matrix form or we're just going to do it in bracket form. What would happen is this would equal to, we will take this part and then we're going to just I'll leave out multiplying in the 1 over square root of 2, but this is going to be multiplied by a 0 here. And on the next line, what we do is we just distribute all of these terms by 0 in here. So this would become, I'll just like multiply them in, get rid of this, and multiply it into each term. Put it in there, put it in there, put it in there, and put it in there. And this is what we would get if we apply a Hadamard to a 0 bit. Now it's not firstly obvious that we would get like what we're expecting to get when we multiply by Hadamard by 0 is this case up here, the 0 plus 1. So that's not extremely obvious right now. But if you remember, sorry, I'm getting a little ahead of myself here. If you remember, do you remember off the top of your head what this inner product does?
It's equal, like if the same value is equal to 1.
Yes.
If it's the opposite, if it's not the same, then it's 0.
Yes, absolutely. So anything and then times x equals to 0. So where x is not equal to, I'll call it x is not equal to 0 is 1. So yeah, absolutely. So when we do this product, you could do it in matrix form to prove to yourself that when you do an inner product a row vector and a column vector, you're going to get a scalar. And when those two like vectors are the same, you're going to get a 1 as a scalar, and when they're different, you're going to get a 0. So if you multiply out this and then add that, what you're going to do is now here the same, so we're going to get a 1. So this term remains. I'll actually do the multiplication out there. So that term remains. Here we're going to get a 0 because we have 1 and 0 in a product. So this is going to be times a 0. And then here it's going to turn into 1 because of the same. And then here it's going to turn into a 0. So that, after we get rid of all the terms that are multiplied by 0, will give us back our, I'll just get rid of these 1s here. This term goes away because it's multiplied by 0. This next term stays because it's multiplied by 1. And the last term gets multiplied by 0, so it goes away. So sanity check checks out. We get our Hadamard back of 0 plus 1 if we did the 0 case. Perfect. So that makes complete total sense. The next one we're just going to do quickly is the x operator here. So the x operator is the matrix 0, 1, 1, 0. So it's even actually easier than the Hadamard case because we're just going to have to only add 2 numbers together. So I'll do that. I'll just do this as a question B. Write that up. Question B. 1, 1, 1, 0, and that's equal to x, which it thinks I'm actually trying to look at the formula, but I'm not. Okay, so this is this matrix. Oh, yeah, sorry, I have to make this a string here. Okay, so yeah, we're going to do an x. So in this case now, all we need to do is add up this case, which is the 1, 0 bra, and the 0, 1 bra and the 1, 0 bra to get this position and this position. So to change this from matrix form to bra form is pretty straightforward. We've already seen the different cases. So it's 0, 1 plus 1, oh, not that, plus 1, 0. And hopefully that is a parent. Let's put that in there. Great. So as exercises for this, like the last of the exercises, I'm going to assign C, D, and E to it. Feel free to do it on paper or to just send it to me typed out. But homework for this tutorial is C, D, or 4.2 to C, D, and E. So this case is the case where it's going to get a little bit bigger because we have a 2 by 2 bit here, but hopefully it's straightforward. I didn't want to assign any of the ones with the XORs in there or the plus or minus because it's starting to get tricky, so we'll just keep it simple and short, just that it's question C, D, and E in addition to 4.1E. So those are the exercises for this week to do. Now we've got a little bit of time, but not too much time. Now that we've worked with projectors and just gotten them a little bit more intuitive sense for them, wanted to look briefly, very, very briefly, at the measurement section in his notes. So this is section 3 here, where we talk about the Bourn rule. So we went over it a couple times in class, but I'll go over it again just as a kind of a reiteration of it. So basically the Bourn rule is stating like when we ask a question with one of these projectors, you get a yes or no answer, and the Bourn rule predicts that the probability of getting a yes is this projector or this function right here. So if you have a projector P applied to a state U, or sorry, phi, that's a little phi there, then the probability of getting a yes for the projector on state phi will be this statement here. And then after the measurement, this collapses to this statement here. So P applied to, the projector applied to the state phi over the square root of the actual function here. So if you were to actually write that out, as we have in class, but I'll write it out again just to make it extremely clear. So this is going to equal to the measurement of probability equals to, so this is going to look like P applied to, and I'm going to write it out here explicitly, phi. That's our little Greek letter with the 0 with a thing through it. I'm pretty sure that's phi. Over, so I'll underline it to make sure that it's over. So that's denoting that there's being divided by. So P divided by phi over phi P, and then phi. So if you remember, for the P, this can be interpreted, this like bottom half, the denominator of the equation could be interpreted as two different ways, because for this, the P could either go to the left side or the P could go to the right side. So this could either equal to this statement here, which I'll copy. So let me look back at the notes just to make sure I got it right. So yeah, the P can be interpreted on either side. Hold up. Yes. So yes, it can go over to this side, so on the left. So that's, so if we give a vector, let me just make this full screen just to make sure. Oh wait, no. This is what I'm trying to look for. This one right here. You can interpret it as xpy or pxy. That's the one. So from our rules, we could take this P out and put it either on the right side, which is, we'll do here, which is P applied to phi, or, oh, it didn't take it because it didn't like that. So P applied to phi, which is just applying that operator, or that projector to the operator, or equivalently, we could also interpret this by taking P and multiplying it on the left-hand side there. So these are all equivalent measurements of the probability after you apply a projector here. So that's just rewriting the thing that I had in section 3. Let me scroll down to it. Oh, hold up. Sorry, lost my train of thought. So yeah, just rewriting this statement here in different forms. So as an example, we can start out with a simple system where we have the 0, 0 state and a projector, or the state phi. We can actually work out what would the probability of getting this would be. So we can work that out just simply, and I'll put this in another Excel spreadsheet here. So I'll make this a little bit smaller. And then here, so I'm going to label this measurement. So here we have a projector, and our projector is 0, 0, 0, 0. So we saw before, if this were to be a matrix, not that we're going to work with them as matrices, but if it was a matrix, we know what that looks like. It's this guy right here with a 1 there, but it's just much more convenient to work with bracket notation. So that's our projector there. And then our state phi is going to be the EPR state right there. So phi is equal to 1 over square root of 2 multiplied by the 2, like the EPR right state there was 0, 0 and 0, 1. So now what we want to do is we're going to want to apply P to phi, so we can get, because this is a very common term that we're going to have on the top and bottom. So let's see what P times phi is, and I know it's worked up in the notes anyways, but let's just do it ourselves just as an exercise. So P times phi, we're going to take this term and then multiply it by this term. I'm going to take the square root and put it out in front just so it's a little easier to read. I'll take the square root of 2 and add it there. I'm going to put this in brackets and then this in brackets. So we're going to be multiplying these two terms together. So this would be equal to this term up here, and we're just going to distribute this. So this is one single term here because it's a bracket there. So what this would actually look like is we're going to apply this term. I'm going to just take this out of the bracket here when we distribute it. Get this there. So it's going to be this there, and then this there applied. So as we remember, since we have things that are the same in the first term, we have the bracket inner product of the same. This can become a 1, and then this part is going to become a 0. So we'll multiply in the next line. So we have this becoming a 1 because it's 0, 0 and ket times 0, 0 bra. So that's a 1 because they're the same. And then 0, 0 times, or 0, 0 bra ket 1, 1 is going to be a 0. Because they're different, and the matrix multiplication will make them different there. So reducing down even further, we can eliminate that 0, 0 because multiplied by 0, and now it's just the square root of 2 times 0, 0 state. So we can see, just as we have in our question here, we get 1 over square root of 2 times the bra of 0, 0. And now if we would actually give the measurement, like what is the probability of this, of measuring a 0 given this projector, or what is the probability of measuring a yes given this projector, we're going to use this version of our Bourn rule up here. So p phi over p times phi. So this, which is going to equal, so this is p phi here, so we got this term. I'll bold this just because we need that a couple different times. So this, there, I'm going to unbold it. So this will be equal to this, and then times this divided by, and I'm actually going to keep doing the same thing where I'll do the top numerator on top, and then put a little bracket here on the denominator. We'll do the same thing. This times this statement, and then we're going to multiply this by phi again, which phi is up here, so we multiply it by phi right there. So again, this is the numerator and this is the denominator. I should make this a little bit longer. We'll do there. So yes, this is the Bourn rule applied here. So we get p phi, which we already worked out on the top here, divided by p phi times phi. I'm just using the right hand, or the very most right hand version of the Bourn rule. And then this will then simplify. I'll copy this, put it down here. So nothing happens to the numerator because the numerator, there's no expression to divide it by. This we can distribute in everything. So this will be 0, 0 will get multiplied into either side of the phi there. So we get 0, 0, 0, 1. So these, because we're doing an well, that's not even an outer product, sorry. Am I doing this right? P phi is that multiplied by phi in bra notation. You're going to get you're going to get a bra times a bra, which I'm assuming is that easy to do? Sorry. Let me make sure I'm doing my math here right. Maybe you want to use the right interpretation of it. P phi by phi and bra. Let me just make sure I got my math here right. So P phi is equal to phi, Let's do in that notation. Let's do in this because the bras and the catch should work out nicer actually. So I'm actually going to multiply this on this side. So that's the phi, and then this is the P phi. So this is going to be phi now in kets. I think I can distribute these into kets instead of bras because the complex, we're taking the complex conjugate of this there. So sorry, yeah, I worked that out that way. So now we can distribute in, so we're going to square root of 1 times square root of, 1 over square root of 2 times 1 over square root of 2 is just 1 over 2 because the two square roots apply in. So that's 1 over 2 in the front there. And then we're going to take the kets, or the bras, and multiply them by the kets. And this we'll do another line of simplification. And on the bottom, this will become a 0, this will become a 1 because of the same. And this will become a 0 here. This is just going to become a 1. So we're just going to get 1 over square root of 2, 0, 0 times over 1 over 2 right here. So we'll get rid of this 1 over 2. So then taking this, we should get a probability of half. I must have messed up my math there somewhere because it's somehow, I must have gotten rid of something that I shouldn't have or applied the wrong rule because I know the probability is supposed to apply out to 1/2. I thought I did that right. I thought that was the way I did that in my notes. Alright, hold on. So this, we have a 0, 0 in the top, which must mean there must be a 0, 0 in the bottom of some kind that we divide out. And when he does it here, P phi P, oh no, but it's the square root of this. Oh, and he's just saying it reduces to 0, 0 there. Yeah, because the square root of that, which becomes, sorry, that's my bad. I completely forgot that there's a square root here. Yeah.
The 1/2's just the bottom.
Yeah, exactly. There we go. That makes more sense. So there's an entire square root over here, which means there's an entire square root over this one, there, and then there's an entire square root over here. And then this becomes 1 over square root of 2 because there's square root on the top and you square root on the bottom. Square root of 1 is 1, and the square root of 2 is there. When we divide that out, this just becomes equal, this just becomes 0, 0 at the end. So it reduces to 0, 0 there. So yeah, we've confirmed that using the Bourn rule, it gets the state, like state yes of 0, 0. So yeah, that was our application of the Bourn rule. And sorry, I'm out of time, so I couldn't get more through. I was hoping to get through more of section 3, but if you have time, read that. If not, but I'm sure we'll cover it in class. But that is today's toils. Thank you for sitting and following along. You just got a few take-homes to do, which is 4.2 C, D, and E, and 4.1, or sorry, yeah, that should be 4.1, not 4.6, 4.1E from the textbook. And yeah, thank you for listening and following along. Any questions before I go, Chris? Or is it pretty straightforward?
That's good.
Okay, yeah, hopefully this is pretty straightforward because it's all matrix multiplication, and then we're using broadcat notation. So, all right, thank you very much.